Hey gang, reaction pathways. It's a very big topic. This video is going to be a slog. I'm going to say probably 90 minutes, but it's a big topic. So there's a lot of rote learning in this topic. And look, over the past couple of years, this one topic has been worth about 9-10% of the EA marks. So pretty big deal. It's tough. There's a lot of rote learning, and you can go into a lot of detail, especially with conditions for different reactions and things. But the odds that they'll really drill you for the specifics, the really obscure specifics, I don't know what the likelihood of that is, but it's good to know regardless. So the way this was taught to me, and the way it's taught in some of the textbooks, is they go by type of reaction. So it might be, oh, here's all the substitution reactions, here's all the addition reactions, here's all the oxidation reactions, and there's some value in that, but a question on the external exam is not going to ask you, name all the substitution reactions, name all the addition reactions. No, the kinds of questions you're going to get, they're going to be, how do we get from compound A to compound C, and in that instance, I think it's far more helpful to have an understanding of, oh, okay, alkane, what kind of reactions do alkanes undergo? Alcohol, what kind of reactions do alcohols undergo? Rather than, here's all the substitution reactions, here's all the addition reactions. So that's how I'm going to move through it, with a few exceptions where it's convenient. One thing also worth noting, so the exam is going to ask you to go from compound A to compound C. How? Maybe you need to talk about the conditions. But the most complex that it's going to get is 2 steps. So it might be, how do you get from compound A to compound C? And the way you get there, you're going to have to say, well, I can go from compound A to compound B, and then compound B to compound C. That's as hard as it's going to get, 2 steps. So in this topic, there is a big picture with everything you need to know, and there's also a small picture with a bit more detail about each type of compound. And I will say, the syllabus does not require you to understand why these reactions occur. That is, it actually says you don't need to know reaction mechanisms. That is how the reactions work. I'm actually going to talk about some of them, briefly, because I think it helps you memorize why the reactions take place, which ones take place, and in some cases it's helpful to memorize the conditions. So if we understand why these reactions are occurring, so just in a little bit of depth, I think it's helpful. But you don't need to recite that in an exam. I'm going to go into more detail than is necessary, not because you need to know that, but to help you memorize or to help you understand these things. That's the tactic I use, and there's plenty of strategies you can use to approach this, but I think it's easier to memorize them the more detail you have. So there's going to be a big picture on this. I've got these 2 whiteboards. There's going to be a big picture on this whiteboard with all the different compounds and everything you need to know, and that's going to be like a flow chart. So I would encourage you, get an A3 sheet of paper or an A4 sheet if you're impoverished, and copy. We're going to copy down a flow chart with all the different reactions that can happen and the conditions. But then on here, and I'd also encourage you to copy this down, 1 type of compound at a time. So we're going to start with alkanes, then do alkenes, etc., etc. We're going to go alkanes, the different types of reactions that an alkane can undergo. Yeah, and I'd encourage you, every time we, get a new page in your notebook or new piece of paper, and copy these notes down too, and write some examples, just to get your head around it. Okay, so to start with, this is the big picture. I want you to we're going to write every class of compound, and I want you to set it out like this, just because it all works out in the end. So top in the middle, we're going to put alkane. To the left of that, haloalkane. Yep. And to the right of that, alcohol. Underneath alkane, pop alkene. Alkene. To the left of that, dihaloalkane. And to the right of that, you're going to put aldehyde over here and ketone, just slightly to the left. Yep, ketone. Then underneath alkene, I want you to put amine, not amide, amine. To the left of that, nitrile. To the right of that, carboxylic acid. Then between these two, just underneath, pop amide. And just over here, ester. And just make that amide plus water. And ester plus water. So make sure you've got that down, and we're going to fill this out with arrows and words. That's the big picture. So like I said, we're going to go one class of compound at a time. We're going to start with alkanes. So pull out a page of notes or a page in your notebook, and we're going to start with big heading alkanes. Okay. Now a big type of reaction that alkanes undergo, and alcohols, that we need to know about is combustion. But that's pretty simple, and I'll just touch on it at the end. We're not going to put it on our diagram because it's just going to complicate the diagram, but we all know combustion. Okay, alkane will burn in oxygen when ignited to form carbon dioxide and water. And we'll go into some detail about that at the end, but it's not going to go in our diagram because it's kind of easy, you know. Alkane or alcohol burns in oxygen to produce carbon dioxide and water. There is one type of reaction that we are interested in that alkanes undergo, and it's called free radical substitution. So free radical substitution. So what is this? What is substitution to start? Well, why don't we draw ourselves an alkane? We'll start really simple. We'll just go methane, CH4. Yeah. So substitution is kind of exactly what it sounds like. We're taking one of these atoms and substituting it with something else. So take this hydrogen atom and replace it with something else. This particular type of substitution, free radical substitution, we learn about it with halogens. So that is your, chlorine, bromine, fluorine, iodine. Free radical substitution with halogens. So that is the reaction of an alkane with a halogen. So let's take chlorine as an example, and remember from, your 9-10 chemistry, the Brinkelhoff twins, these diatomic molecules, bromine, iodine, chlorine, oxygen, fluorine, they roam around the atmosphere in pairs, diatomic molecules, 2 atoms. So we have this, halogen, and what we've really got is 2 halogen atoms, and this is reacting with this. So we want to substitute one of those hydrogens for one of those chlorine atoms. And this whole free radical substitution thing comes in. Well, how are we going to do this? So in order to replace this hydrogen atom with a chlorine atom, first we need to break this bond. Yeah? We need to break that bond so we have 2 individual chlorine atoms, not the diatomic molecule. And the way we do that is we have some UV light or some heat, or both. So that's the conditions for this reaction to occur. UV light or heat, because we need to break this bond somehow. And when we break that bond, we have what we call free radicals. So they're these two chlorine atoms that the bond is broken, but they're both ready to form a bond now. So we call them free radicals. They're really eager to form a bond. And in fact, they're so eager that this one is going to go ahead and bond with the carbon atom, and that hydrogen is going to get kicked out, and it's going to bond with this chlorine atom. So now they've both got a friend, and what we end up getting is chloromethane. So we've substituted the hydrogen, and importantly, there's a byproduct. So HCl, in general, we're going to get a hydrogen halide. So HCl, HBr, HI, but obviously HCl, well, that's hydrochloric acid, isn't it? So alkane plus halogen gives you haloalkane plus hydrogen halide, yeah? And that's just an example. That's methane plus chlorine gives you chloromethane plus hydrochloric acid. And the condition for this reaction to occur is UV or heat, because we need to break that diatomic molecule into two chlorine radicals. So that's just an example. Let's rub that out and give you a word equation to put in your notes. As I said, alkane plus halogen gives you haloalkane plus hydrogen halide. Yes, like HCl, HBr, HI. Okay, let's put that on the big picture then. We're going from alkane to haloalkane. And that type of reaction is, we're going to call it free radical substitution. And the conditions are, this is important, UV or heat. Now, importantly, this reaction is not very useful. So if I go back to that example before, or I might do a slightly different example. Say we have propane, yep, lots of hydrogens, and you know, for the heck of it, let's do chlorine again. So what is the product that we are going to get exactly? Well, the first limitation of this reaction is that, you know, once I split up those chlorine atoms, I could replace this hydrogen with chlorine, but, you know, I could replace the one in the middle, or, you know, and the one on top, the one on the bottom. There's no guarantee as to which hydrogen is getting replaced. So we might get what's called, you know, structural isomers, positional isomers. It could be on carbon 1 or carbon 2, if you get that. And the other issue is, say we've already done this reaction once and we've now got a haloalkane. So say I substituted this one for chlorine. There's nothing special about that. This can react again with the chlorine, and now we've substituted this one. What's that? We've got a dihaloalkane now. And, you know, that's not what we wanted. And this can react with this again, and now we've got a trihaloalkane. So haloalkanes can themselves undergo a free radical substitution with a halogen, and that can form a dihaloalkane, trihaloalkane, tetrahaloalkane, and so on and so on. Hell, we could have all Cl's, no H's left, you know. So what you end up with, inevitably, is this, you just end up with a mixture. You don't just end up with haloalkanes, you end up with structural isomers, you end up with dihaloalkanes, So yeah, it's not a very specific reaction would be the term. And just to, just write that one down. So haloalkane, I know this isn't technically an alkane, but it is the same reaction. So haloalkane plus halogen gives you a dihaloalkane. And importantly, there's still hydrogen halide because the other ClCl, the other Cl atom bonds with the hydrogen that we took off the alkane. But the conditions are the same. So we still need that UV or heat. Well, I didn't write them on the other one. Write them on the other one, please. So we still need that UV or heat to break the diatomic halogen into two radicals, yeah? So I'll just pop that one on the big picture as well. And you will sort of see, this is the same reaction that's happening really. But I'll put it on there because it looks nice. So free radical substitution. A bit messy, sorry. Just go free rad sub. Yep. And the conditions are still UV/heat. So it's the same reaction. And it doesn't end there. Remember, dihaloalkane could become trihaloalkane. Trihaloalkane could become tetrahaloalkane. You get it. So not a very good reaction. You're going to end up with a mixture. I'm just going to even put an arrow there. Can react again. Yeah. That is it for alkanes. So next I think we'll do alkenes. Yeah. So these alkenes, if you recall, they contain at least one double bond. That's the definition of an alkene. They are unsaturated, whereas alkanes are saturated, alkenes are unsaturated. They contain at least one double bond. Now to get you thinking about, why do alkenes react in the ways they do and alkanes don't? I just want you to think about, well, what is a double bond? So let's just draw ethane, yeah? Single bond. Alkane, ethane, single bond. And you've got CH3, CH3. I'll even draw those on. So, ethane. Now just to really simplify this and go, well, what's actually happening here? This is a very simple representation, but we know the electrons, maybe from year 10 or 11, we know the electrons are in orbitals, these funny shaped orbitals, and they have different probabilities of, being around the nucleus of the atom. So if I just draw what those orbitals, a really simple representation of what they might look like. I'll draw the orbitals in blue. These are where the electrons live. So there's one coming off there. And remember, every atom wants to have a full octet of electrons. So they want to have 8 sort of electrons or 4 electron pairs. So each one of these little teardrops is going to represent an electron pair. So you can see this bond is a direct end-to-end overlap between these two orbitals. So this is a very strong bond. And you can rotate that bond. We call this direct end-to-end overlap between orbitals. We call that a sigma bond. And yeah, you can rotate freely around it. It's a very strong bond. It's kind of very, very direct. Now, what happens when we go, okay, we're not talking about ethane anymore. We are talking about ethene. That is, we are adding a double bond. So what is this double bond? What does that look like? Well, if we look at our orbitals, none of the other ones have this direct overlap. So what we end up with is these two orbitals above or below, they're parallel. They have this side-by-side kind of interaction happening. Even though they're not, they're not touching, there's this parallel sort of interaction happening, or side-by-side, if you will. So while a sigma bond is end-to-end, this extra bond that we've just added, we call that a pi bond. And it's a side-by-side kind of parallel interaction between orbitals. And you can see, well, this one looks a lot easier to attack than this one. This is much further out from the sort of center of what's going on here. So, something that was really keen to break this bond could do so very easily. That is, the pi bond is much more readily broken than the sigma bond. And the same kind of goes for triple bonds. Like a triple bond is just another sigma bond down here, that's a triple bond. But yeah, we don't need to talk about alkynes, just alkenes. So if that's what you're thinking about the types of reactions that we might see with alkenes. And yeah, one reaction that involves breaking the double bond, or breaking that pi bond and turning it into a single bond, it's called addition. So addition reactions. So if I just give you that ethene molecule again, what an addition reaction is doing, it's breaking that pi bond that's further out from the, atoms, breaking that one, and now each carbon is only forming 3 bonds. So we have one new bond on each carbon to form to a new atom. So we can add in something here, add in something there. That's why we call it addition, yeah? And there's quite a few different things we can add, and there's all different conditions that sort of apply to each thing we add. Now the obvious one is, okay, well I have an alkene, say ethene. How do I turn this into ethane? What am I going to add? Well, it's missing 2 hydrogen atoms. So if I added 2 hydrogen atoms, or H2, yeah? Let's break this bond, add in a hydrogen, we get ethane. So we're adding hydrogen across the double bond. Note that there's no byproduct. The same number of hydrogen atoms on this side, same number of carbon atoms on this side. No byproduct. We can think of that as alkene plus hydrogen gives you alkane. So that's an addition reaction. We call it hydrogenation. The QCEE actually classify this as reduction because, yeah, there is a gain of electron involved. There is a gain of electrons involved. So yeah, you can classify it as reduction, addition. Good to know. There is one condition for this to occur. So it's not just going to occur automatically. And it's what we call a metal catalyst. So you know what a catalyst is. And some examples of what kind of metals we might use. Platinum, palladium, nickel, right? So what actually is a metal catalyst? We don't have some test tube and we're putting in some platinum filings and giving it a shake. Like that's not really how that works. It's more, you can sort of imagine this, we've got some gases floating around. Like we've got ethene gas, we've got hydrogen gas, we're like forming a ethane gas, yeah? So we're going to have these sheets of metal, and if you think about what a catalyst does, well, catalyst increases the rate of the reaction by allowing more collisions to occur in the correct orientation, you know, more effective collisions. So that metal catalyst is giving these gas particles something to sort of cling on to and hit each other in the right orientation. That's what a metal catalyst is, these sort of sheets of metal in your reaction vessel that these gases can kind of, you know, cling onto and use as exactly that, a catalyst to give them the correct orientation. So that's the one condition that you need, a metal catalyst. So let's put that in your notes as a word equation. You should definitely be copying these down and have an example for each of them. Maybe come up with your own example. So that's alkene plus hydrogen gives you an alkane. And I'm going to put the condition in blue, which is metal catalyst. Platinum or palladium or nickel. Yep. Okay, what else can we add? Well, let's take that ethene again. Okay, what about a halogen? So, let me go bromine, yeah? Remember diatomic, Brinkelhoff? I think you should sort of see what's going to happen here, yeah? It's an addition reaction. We're going to break that pi bond. And bromine going to go there, bromine going to go there. It could go on any of those, you know, positions as well. Just be aware of that. So it could be up here. We've added 2 halogen atoms, so we're going to get a dihaloalkane, yeah? C. Well, maybe I'll put one up there, one down there. H. So, we've got ethene plus bromine gives you 1,2 dibromoethane, yeah? Again, no byproduct. We haven't taken any atoms out, we've only added atoms in. The thing about this reaction that's really important, very important, is there are no conditions for this. The halogens are quite ready to react. They like reacting, and there's no conditions for this reaction to occur. It'll just occur. And that's really important because we use this reaction as a laboratory test. Let's just say you have a solution and you're like, man, I'm not sure if this is an alkane or an alkene/alkyne. That is, does this contain single bonds or does it contain double or triple bonds? And we can use this reaction to tell because it has no conditions. So say we have a solution of bromine water. Bromine water is brown, yeah, it has a brown color. If we add a alkene with a double bond in there, this reaction is going to happen. So this stuff is going to become 1,2-dichloroethane, for instance. It's not bromine anymore, it's going to lose its color. It's becoming this. So this won't be brown, this stuff's brown, but we're using all that and it's going to become colorless. So in other words, if we have an alkene or an alkyne, the bromine water is going to lose its brown color. If we just had a single bond, so if we just had ethane or any other alkane, this reaction would not happen. We would still have bromine water and it would keep its color. So it's an important laboratory test to tell apart alkanes and alkenes or alkynes. So yeah, let's write that one down. That is alkene plus halogen dihaloalkane. No conditions. Not writing anything there. No conditions. Put it on the big picture. So we're going from alkene to haloalkane. Alkene to dihaloalkane. there yet. Yeah. No conditions, but it is, of course, an addition. Oh, let's put alkene becoming an alkane as well. So alkene plus hydrogen gives you an alkane. And that's, we call it a reduction reaction really. And the condition is metal catalyst. Yep. Can I encourage you, if you have enough space, say you have A3 paper, on these arrows, write the full word equation as well, because then you know what your reactants are. Yeah. So that's those two addition reactions. We can also add, those aren't the only things we can add. We can add water. I'm going to do something a bit different. Instead of ethene, we're going to go propene. And you'll see why in a second, something a bit harder. We call this an asymmetrical alkene. It's not symmetrical, there's a double bond on this side. There's no double bond here. It's not, no symmetry. And that's important, and you'll see why in a second. So we're adding water. Now, you can think of water H2O, HOH, but how we're going to think about it now is HOH, two different things, HOH. In other words, we're going to break this double bond, and we're going to put H on one side and OH on the other side. Yeah, we've added water. We call that hydration. So what's that going to give us? Well, an alcohol, yeah? OH, alcohol, hydroxy, functional group. So CCOH. Or, ethanol. No, sorry, propanol. We've got three carbons, haven't we? So C, C, C. And you see the OH is on the second carbon, so OH. So that would be 2 propanol. Yep. Propene, 2 propanol. Now, why did I use an asymmetrical alkene? Why did I use an asymmetrical alkene? Well, see, I've put the hydrogen on this carbon, and I've put the hydroxide on this carbon. Could I not put them on the other way around? And yeah, I could, absolutely. No one is stopping that from happening. Say the OH was there and the H was there. Well, all of a sudden, I have a completely different product. So the OH is there. So we've got propan 1-ol now and propan 2-ol. And they can both form. They can both form, that's completely possible. And they will both form, and we will end up with a mixture, right, of, you could call them structural isomers, positional isomers. The functional group is on a different position, yeah? However, there is a thing called Markanov's rule that says one of these products is going to be favored, to a great extent compared to the other. We're going to form much more of this one, as it turns out, rather than this one. And the reason why is you don't need to be able to explain Markanov's rule. So you can just think of it like this, I suppose. When we're adding a hydrogen to a molecule, so to an asymmetrical alkene, yeah? Because if this was symmetrical, say this was just 2 carbons long, well, this would be the same, yeah? Like it'd be carbon 1 and carbon 1. We could just flip it around. There would be no isomerism, so it wouldn't be a big deal. So this only applies for asymmetrical alkenes when we're adding 2 different things. Markanov's rule is basically the hydrogen will go to the carbon where there are already more hydrogens. This hydrogen wants friends, wants as many friends as possible. So on this carbon, it's already got 2 friends. On this carbon, only got 1 friend. It wants to go to where the party is, so it's going to go to this carbon. So yes, it is actually going to be H on that one, OH on that one. Most of the time, you will still get some of this. So you will still get a mixture, but we call this the favoured product. Favoured product, main product, whatever you want to call it. And that's Markanov's rule. Hydrogen will go to the carbon where it has more friends. And I'm gonna use the green pen, the green asterisk is gonna mean Markanov's rule. So let's add that to your notes. So alkene, alkene plus water gives you alcohol, but it will give you a mixture of alcohols. So use Markanov's rule. There is one condition for this. Oh, hang on, no. There's a couple of conditions for this reaction to happen, and they are: we're going to need a high temperature. So high temp. You're also going to need a high pressure. So really, we're adding energy. These reactants need energy to react. We're increasing how fast they move, temperature. We're increasing the pressure to make more collisions happen. High pressure. And we actually need what's called an acid catalyst. Could be like, sulfuric acid or something. So acid catalyst. Yep. Let's add that to the big picture. Alkene becoming an alcohol. Let's do that. We also call this reaction, we call this hydrogenation, addition of hydrogen. We can call this hydration, addition of water, just, for fun. But it is an addition reaction. And the conditions are temperature, T, high temperature, high pressure, P, and acid catalyst. Yep. Now there is one more thing that we can add across the double bond, and that is a hydrogen halide. So those hydrogen halides that we were forming earlier as a byproduct, like HCl, HBr, HI, let's think about, let's use propene again as an example, because it's asymmetrical. This is important again, and you'll see why. So we've got propene. We're going to add a hydrogen halide across the double bond. So let's go HBr. You might see where this is going. Let's break that. Bing, bing, bing. H. Bing, bing, bing. Br. Adding 2 different things to an asymmetrical alkene. So the H could also be here. And the Br could be there. And there will be a favoured product. Again, Markanov's rule is going to apply. Both products will be formed, but one of them will be favoured. And you can see, well, over here, the hydrogen has more friends. So this is going to be the favoured product. Which, let's see, that's 2-bromopropane, sorry. Yeah. So propene plus hydrogen bromide, 2-bromopropane, or the Br could also be there. So that would be 1-bromopropane. 2 bromopropane, 1 bromopropane. And as we know, Markanov's rule says that we're going to produce much more of this. That is the favoured product. Yep. There are some conditions for this one to... Oh, well, there's one condition, sorry. You know, as I said, the halogens like to react. Except if we've got water present, we're going to get some of that occurring. So if we just want this to occur, the condition is that there is no water in our reaction environment, or we're going to get some hydration occurring as well. Let's add that one to your notes. Alkene plus hydrogen halide gives you a haloalkane, not a dihaloalkane, just one. And again, asymmetrical alkene, and Markanov's rule applies. And the condition? No water, or we're going to get some hydration occurring as well. Add that to your diagram. Let's just put on this reaction that Markanov's rule applies. Put some green on there, yeah? So what we've just done is alkene plus hydrogen halide gives you a haloalkane. It's going to get a bit busy up here, isn't it? I hope you've got lots of space on your A3 paper. So this one is addition, and the condition is no water, or we're going to get some of that happening, you know. Okay. Just one thing I want to mention about this one. Obviously, if we're reacting with water, the water needs to be in excess. And we're talking about high temperature and high pressure, so this water, it's actually going to be steam. Probably worth mentioning in your response. If you're doing this water reaction at high temperature and high pressure, you can have steam, yeah? So, yep. That's your last addition reaction for alkenes. But. Not going to go into too much depth here. There is, say we just had ethene. And maybe a catalyst and high temperature and high pressure. We don't have any other reactants. Well, we're still going to break that bond. It's got nothing to bond to, or does it? Because we've got more than one of these. Yeah. Got nothing else to react with. And all of a sudden, these guys are joining together, and he's joining with another one. And that's polymerization, so just worth thinking about. Polymerization is self-addition. That would be polyethene. Ethene monomers adding themselves to each other, and you know you'd represent that like C, your repeating unit thing. Yeah, that's polyethene. Just worth thinking about. Self-addition, you'd call that. Not part of this topic, but there's a connection there. That's it for alkenes. So next we're going to do haloalkanes. We have already done one haloalkane reaction, if you remember. It's this, how an alkene could become a haloalkane, but then a haloalkane could become a dihaloalkane, which could then become a trihaloalkane. But we're going to be focusing on haloalkanes now. So new page in your notes, big heading, haloalkanes. Now, haloalkanes are capable of undergoing a new type of reaction, and we call it nucleophilic substitution. So it's still substitution. You know, we did substitution before when we added a halogen free radical, like a chlorine atom, to an alkane to form a haloalkane. We did that before. That was free radical substitution, where we used the UV light to split the diatomic chlorine into two. This is a little bit different, and it arises from the idea that we have a haloalkane now. It's not just a normal alkane. So this is ethane, and if we draw the bond dipoles, if you remember from year 11, we draw the bond dipoles on that. And keep in mind, in 3D, this is a tetrahedron. It's not like a square, but they're all pointing in to the carbon, so they cancel each other out. There's no dipole on this molecule. It's not polar. But say I have a haloalkane now. Say I have bromine up here. Well, we know bromine, all the halogens, are very electronegative. It's going to be much more electronegative than the carbon. So what we're going to have a big bond dipole all of a sudden, and the net dipole is going to be going upwards. What does that mean exactly? Well, this guy, he's electronegative. He likes electrons. He's hogging the electrons, so he is partially negative, yeah? Which leaves this part partially positive. Bond dipole, partially positive in here, partially negative in there. Now, why is this important? Why is this important? Well, what if we had something that really liked positive things, even more, more than this guy liked positive things? We'd call that a nucleophile, attracted to the positive center, the positive nucleus of this whole arrangement, attracted to that nucleophile. So let's just say Nu for now. Let's just put a negative charge on it. It doesn't have to have a negative charge, but it makes sense. Negative attracted to positive, yeah? So this guy likes the carbon atom so much that's got the partial positive charge that he just kicks the bromine out, and now we're going to have Nu up here, and the bromine got kicked out. So he's an ion now, Br minus. Yep. So Nu would be a nucleophile, and I'll show you some examples of nucleophiles. But yeah, we can represent that generally. So our nucleophile, let's call him Nu minus. Again, doesn't necessarily have to have a negative charge. I'll give you some examples. So if it has a negative charge, yeah, it's probably a nucleophile, because obviously negative things like that positive nucleus, or that positive part of the bond. So OH, hydroxide, got a negative charge. Cyanide ion, that looks like that, triple bond between carbon and nitrogen, also got a negative charge. It doesn't have to have a negative charge, so if you think about something like ammonia, NH3, doesn't have a negative charge, neutral molecule, and as we know, nitrogen forms 3 bonds with hydrogen. But there is a non-bonding pair of electrons here. If we remember the whole octet rule thing happening, yes, it forms 3 bonds, but it has a non-bonding pair of electrons that doesn't form a bond. This part of ammonia is still negative. It's 2 electrons with nothing else there. There's this negative part of ammonia, and as it turns out, because it's negative, it really likes positive stuff. So that non-bonding pair of electrons makes ammonia a nucleophile, even though it doesn't necessarily have a negative charge like these guys. So the nucleophile reacts with a haloalkane, so that's some kind of carbon chain, and X is any halogen atom, like Cl, Br, I, whatever. Reacts with that, we think about what's happening. This guy decides he likes the partial positive end of the bond. This part's partial positive, partial negative, more than X does, and X gets kicked out. So we end up with R plus X minus, bonded to the nucleophile now. Notice that it doesn't have a charge anymore because it's formed that bond that it was trying to form. It's now sharing that electron, whereas this guy is now an ion. It's got kicked out, it's not forming a bond anymore. That's just a way to think about nucleophilic substitution. Again, you don't need to know about that, but it helps to know how these things work, to remember them. So yeah, let's think about some of those nucleophiles we were talking about before. A good one is a cyanide ion. So let's say we've got that is a red pen. Hang on. Okay. Let's go, we've got some haloalkane. Let's go 1, 2, 3, Br. Bromo, propane. And let's react that with a nucleophile. Cyanide ion. C triple bonded to N. Got a negative charge. What are we going to get? I haven't drawn in the hydrogens. You could draw those in if you want. But what we're going to see is, okay, this bond, partially positive over here, partially negative over there. This guy's negative. He wants to bond to that. So we're going to get C, 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 N plus Br minus. Really important. Look, we've just increased the length of the main carbon chain by 1. So we had bromopropane. We now have but, change the prefix, 4 carbons now, butanitrile. We formed a nitrile, yeah? But yeah, and you've got a bromide ion now. Something of note, if you were writing this in an exam question, obviously in a solution you don't just have ions on their own. So you don't have cyanide anions without a cation. So you might have potassium cyanide, K plus Cn minus, potassium cyanide, which would mean that the bromide ion is hanging out with the potassium ion once the reaction is done. Yeah, so that they're always in pairs. Let's write that one out as a word equation. So that is haloalkane plus cyanide ion gives you a nitrile, yeah? And halide ion. So the halogen is an ion. Halide ion with a negative charge. There are some conditions for this one to occur, so it needs to occur in what we call reflux conditions. Reflux conditions. What is that? Well, I don't know if you know what acid reflux is, not the most pleasant analogy, but we've got a solution here and we're heating this solution, so it vaporizes, right? Slowly. But once it vaporizes, we are cooling the vapor, so it condenses back into liquid form and drips back into the solution. The way that normally happens is, you might have done this in a prac maybe, is you've got some kind of vessel, you're heating it with the Bunsen burner, but it's a closed container and you're collecting all the gas, and there's a little tube that you're pumping cold water through, and the gas comes up and touches the cold water, condenses, then drips back down into the solution. So reflux conditions, in other words, it's the constant transition from liquid to gas, back to liquid to gas, back to liquid to gas. That's reflux conditions. So you need that, yeah. And you also need an ethanol solvent. Yeah. So let's put that on the big picture. By going from a haloalkane to a nitrile, so big arrow, haloalkane to nitrile. Now, that is a nucleophilic, I'm just going to write NOC nucleophilic substitution reaction, and reflux conditions, and ethanol solvent, ethanol. Get a nitrile. Okay. What other nucleophiles can we deal with? Well, we were just talking about hydroxide ions, which are, of course, a nucleophile. So let's take 1-iodo propane, yeah? And let's react it with hydroxide ions. Nucleophile, I think you see where this is going. This guy's going to get substituted for this guy, and he's going to become an ion. So CCCOH plus I minus. Again, maybe you'd have a sodium ion. So this guy needs to have a cation, so it might be Na, sodium hydroxide, sodium iodide. But it could happen with, any group 1 metal, so don't worry too much about that. We've got a haloalkane reacting with hydroxide ions. It's forming a alcohol. There you go. Now, there is another type of reaction that has the exact same reactants, but different products, and it's an elimination reaction that haloalkanes undergo. So how do we determine whether this reaction is going to occur or this other elimination reaction? And the answer is the conditions for this reaction are so specific. They are so specific. That's how you remember them. You remember, oh my God, this one has, and the other one have extremely specific conditions. The first condition, well, in some circumstances, this reaction is far more likely to proceed. In other circumstances, the other reaction is far more likely to proceed. And let me just explain briefly. You may recall primary, secondary, tertiary haloalkanes. A primary haloalkane, the carbon that is attached to the halogen is attached to one other carbon. So that's primary, and we write it like that, 1 degree, yeah? Secondary haloalkane might be, let's just do 4. So now the carbon that the halogen is attached to is attached to 2 other carbons, secondary. And finally, say we put a methyl group there, sorry, that is a C. Say we put a methyl group on this carbon and the halogen on that same carbon. Well, now the carbon that the halogen is attached to 3 carbons. It's a tertiary haloalkane, yeah? That's important. That is very important for this reaction because this nucleophilic substitution reaction is only going to happen for primary or secondary haloalkanes. Yeah? Now, there are some other conditions. I'll put that in blue because it's a condition, yeah? So primary or secondary. These need to be, so they don't need to be, but the preferred conditions for this reaction are dilute hydroxide. So say you used sodium hydroxide, you'd want to use dilute sodium hydroxide, like 0.1 molar instead of 1 molar. This also occurs in reflux conditions. And this one is a real head spinner. You need a 50-50 ethanol water solvent. So half ethanol, half water solvent. I'm sorry, there's no way to, well, there probably is some way to understand that. I don't understand it. But I do remember it by going, gee, this one's really specific. I need to know this one, or elimination is going to occur instead. So yeah, let's write that down. So haloalkane, and that is a primary or secondary, not tertiary, plus hydroxide ion gives you an alcohol plus a halide ion, of course, yeah. The leftover, the halogen atom that we kicked off. You get that halide ion. And those conditions, if we recall, reflux, those have got to be dilute hydroxide ion. And of course the wacky 50-50 ethanol water solvent. Woohoo. Let's put that on the big picture. Now this one is, we're going to put an arrow up here. That's what we're going to do. So haloalkane to alcohol. That is a nucleophilic substitution because the hydroxide ions are negatively charged. They're a nucleophile. And the conditions, reflux, dilute hydroxide ions, and the 50-50 ethanol water solvent. Yep. Okay. There's one more nucleophilic substitution reaction. Then we'll talk about that elimination reaction as well. But as we said, ammonia, NH3, even though it's not negatively charged, is still a nucleophile. So let's go CCCBr, 1-bromopropane, plus NH3. Remember that this has a non-bonding pair of electrons, so it's a nucleophile. What's that going to give us? Well, if this thing's getting substituted for this, we would get CCCNH3. But that doesn't make sense, because nitrogen only forms 4 bonds. And what's this guy going to form a bond with? So really what happens is we get CCCNH2, we remove one of the hydrogen atoms to make room for the bond, and that leftover hydrogen atom forms a bond with bromine. So we get a hydrogen halide, hydrogen bromide. So if I write that out, it's CCCNH2, nitrogen forming 3 bonds, great, plus the leftover hydrogen, HBr. Haloalkane plus ammonia gives amine plus hydrogen bromide. Now, there's a problem with this. There's a big problem with this. We've just formed a primary amine, yeah? Similar to haloalkanes? Well, no, not really. Primary amine is the nitrogen atom is attached to 1 carbon chain, yeah? Secondary amine, you might have another one coming out, yeah, like C. Tertiary, you'd have 3. But we've just formed a primary amine. This is still a nucleophile. That nitrogen atom still has a non-bonding pair of electrons. Excuse me. still has a non-bonding pair of electrons. So this is now competing with the ammonia. They're both nucleophiles. It's competing with the ammonia to be substituted. Both nucleophiles. So this original reactant could react with our product. And all of a sudden, we've got a secondary amine happening. So C, 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 and H. Remember, we've taken off one of the H's here. C, 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 plus HBr. And I think you can see by now, still a nucleophile. This could happen again, and we'd have another one sticking out there, have a tertiary amine. So what we're going to get a mixture, another mixture of primary, secondary, tertiary amines. It's a little bit useless, not a very specific reaction. But yeah, let's write it out, and we'll get to the conditions. So haloalkane plus ammonia gives you an amine plus hydrogen halide. Yep. Now I'm going to indicate in green. There's no Markanov's rule we can apply here. Completely different thing, but it is a primary, secondary, tertiary mixture that you end up with. The conditions are: you want lots of heat, and you also want pressure. And the way we do that, we're talking about gases here. So if we put the gases in a sealed tube and just heat them up, gases in a sealed tube heating up, of course we're going to increase the pressure, because the hotter the gas, the more space it takes up. So put in brackets, sealed tube, or sealed vessel. Yeah. And we need an ethanol solvent. Yeah. Okay, the last reaction we're going to talk about, it's not nucleophilic. Oh, before we do that, let's pop this one on the big picture. So we're going from haloalkane to amine. Going to be a bit of a wacky arrow. Yeah. That is also nucleophilic substitution. And the conditions, as we discussed, are heat. I'll do like temperature, T, pressure, put in brackets, sealed tube, and ethanol solvent. Okay, the last reaction of haloalkanes we're going to talk about is that elimination reaction. So remember, this haloalkane plus hydroxide ion gives alcohol plus halide ion. It's only going to occur if we've got these very specific conditions met. There's another set of conditions where we're going to have what we call an elimination reaction. Now this also involves a hydroxide ion, which is why there is the same reactants. It's a bit of a complicated so an elimination reaction, it's basically we're removing an atom. Let's take our haloalkane. That's a good example. I'll do a tertiary haloalkane. You'll see why in a second. So CCC Br, the carbon that the halogen is attached to attached to two carbons, tertiary, and I'll put on the hydrogens. So an elimination reaction is when we take two adjacent carbon atoms, could be these ones, I think you'll see it's the same because this is symmetrical. would be the same molecule. But we're taking two adjacent carbon atoms and we're removing one atom from each, removing an atom to form a double bond. Each of these can now form an extra bond. Well, we better do something about that and chuck in a double bond. Sorry, I'll put that in blue to show that it's new. Removing an atom from two adjacent carbon atoms to form a double bond. Yeah? So that would be a haloalkane becoming an alkene. Now, I didn't do a tertiary amine. Let's redo that, but I'll do a tertiary amine in my example, and I'll show you why. So what is happening here, and how, the atoms don't just fly off into free space. Where are they going? And that's why we need a hydroxide ion. So let's draw. So there you go. I'll put the bromine up there actually. So what have we got here? We've got 1, 2, 3, 2 bromo, 2 methyl, propane. Yeah? Tertiary haloalkane. This carbon is attached to 3 carbons. Now, 2 adjacent carbon atoms, just like before, we're going to remove an atom from each adjacent carbon atom and put in a double bond. Yeah? Now, this involves a reaction with hydroxide ion because this hydrogen atom goes ahead and forms bonds with that to form water. Hydrogen plus hydroxide, water. That's why we need our hydroxide ions. Because where is the hydrogen atom going to go? Now on the other side, what have we just formed? Well, we've formed an alkene. So it's going to give us an alkene, which would be, 2 bromo, just 2 methyl propene. So 1, 2, 3, methyl, 2 methyl propene. C. Got the methyl group, got the methyl group there. We've formed water. And the last thing we have left is the bromine, which is going to form a bromide ion? Yes. So remember, this might be with sodium hydroxide. This would form sodium bromide. Yeah. That's the mechanism. You need hydroxide ions because the hydrogen atom will bond with it to form water. That's why you form water in an elimination reaction. Now, let's write that out as a word equation. Haloalkane plus hydroxide ion is going to give you an alkene plus halide ion plus water. Same reactants as this one, different products. How do we determine which one's going to happen? Well, as I said, the conditions are different. So we had dilute hydroxide ions here. We're going to have concentrated hydroxide ions here. Reflux, they're both in reflux, so also reflux conditions here. Instead of a 50-50 ethanol water solvent though, we're going to have just an ethanol solvent. 100% pure, delicious ethanol solvent, yep. The other thing is, remember we said this occurred for a primary or secondary haloalkane. This reaction occurs for a secondary or tertiary haloalkane. So in other words, if you've got a primary haloalkane, you're probably going to have a nucleophilic substitution reaction that happens. If you've got a tertiary haloalkane, you're probably going to have an elimination reaction that happens. If you've got a secondary haloalkane, it could be either, and you've really got to look at the very specific conditions, yeah? So, let us put that on the diagram. We've got haloalkane forming a alkene. So we're going to draw another arrow back. Haloalkane, back to alkene. Got it? See, it can go in both directions. So addition in this direction, elimination in that direction, forming a double bond, removing two atoms from adjacent carbon atoms to form a double bond, alkene. So that's elimination, and your conditions are concentrated hydroxide, and reflux and ethanol solvent, ethanol solvent. I really hope you have more room than I do. This is a bit of a mess. You know what I've realized is when we did this is a addition reaction. So when we added water across the double bond in an alkene, HOH. No, sorry. When we added a hydrogen halide. See, I'm getting tired. It's a long lecture. Let's reset. Let's take a breather. You with me? Okay. Alkene to haloalkane. Addition reaction, we were adding a hydrogen halide across the double bond, like HBr, for instance. H on one atom, Br on the other atom. We go from alkene to haloalkane. If it's asymmetrical, we're adding two different things. Remember Markanov's rule. So for this reaction here, we've got Markanov's rule applying, yeah? That's it for haloalkanes though. That's it. Let's talk about nitriles. I will just mention, you would have noticed haloalkanes, there's a lot of reactions for them. So when I was talking earlier about on your EA, the most complicated that it's going to get is you've got to get from compound A to compound C, and most complicated it's going to get is you've got to go compound A to compound B from compound B to compound C. Compound B is quite likely going to be a haloalkane, just because there's so many things you can get from it, yeah? Compound B, though, could also be a nitrile, because they have a very handy reduction reaction, nitriles have, if you want to form an amine. So nitriles, new page in your notes, new heading. So, let's get a typical nitrile. Let's get ether nitrile. Yep. Now, we can form an amine from this. It looks a little bit like an addition reaction, but remember that when we were adding hydrogens to an alkene across the double bond, we called it a reduction reaction. Similar thing happening here, because there's a gain of electrons involved. And if you wrote out the oxidation states, you would see this. But it's really like, it's a bit of an addition reaction. We're breaking one of these bonds. So we're actually breaking two of them. First we break one of them. So we've now got, okay, so this guy can form a bond with, let's say, hydrogen. This guy can form a bond with hydrogen. That's still not an amine. An amine still has a single bond. So if we broke this one as well, now I've got another hydrogen there and another hydrogen there. So we've got ethanamine, primary amine, yeah, NH2. So let's write that out as it was. Got ether nitrile plus, you'll note we just added 4 hydrogen atoms. So if we're going to be balanced about this, 2 H2. We're breaking 2 bonds, adding 2 lots of hydrogen atoms. That gives us CC NH2. Yeah, and there's, you've got your hydrogens happening there. So ether nitrile plus hydrogen, ethanamine, primary amine, yeah? We don't have a mixture of amines. So if you remember, when we were forming amines from haloalkanes, yeah, by the nucleophilic substitution of ammonia, remember that our products were nucleophiles and they were competing for substitution. So we'd end up with a mix of primary, secondary, tertiary. Not a problem here. Where are we going to add the hydrogens? Yeah. So if we want to form a primary aliphatic amine, this is your go. So say your product A, you've got to get from haloalkane to primary amine. Well, compound A, haloalkane, convert it to a nitrile, compound B, and convert the nitrile to an amine. Yeah, very specific. Best way to do it. There are conditions for this though. So usually, the usual way to do it is we use a metal catalyst. We talked about that before. Metal catalyst. And we need heat and pressure. Yeah? Not too hard. So let us write that one out. Nitrile, well, we'll put it under reduction as well. Because yeah, that's what we call it. It looks like addition, but we call it reduction. Reduction, nitrile plus hydrogen. And that would give you what? Amine. We'll put primary amine plus nothing. And your conditions, of course, are metal, catalyst, and heat, pressure. There is another way we can do this. Same thing, nitrile to amine. A little bit complicated, so probably worth taking notes on this. This is a full chemical equation. This is not a half reaction, but it is a reduction reaction. We can use a reducing agent called lithium aluminium hydride to achieve the same effect. So if we have, I don't know, some kind of, let's just use ethanitrile again, ethanitrile. Reduction half reaction. This reaction is not complete. Yeah, half reaction, and then we'll get CC and H2, and with all the H's, yeah, ethanamine. we can use a reducing agent. So the reducing agent would be oxidized, and that reducing agent, we call it lithium aluminium hydride, LiAlH4. So all the hydrogens, H4, those 4 hydrogens that you need, are in this reducing agent, and there's an oxidation half reaction involving that that would of course occur. So when you're describing this process, this is not a complete chemical reaction. Obviously, you can see there's atoms there that aren't there. But this is reduction using a lithium aluminium hydride reducing agent. Yeah, that's a very expensive chemical, apparently. So in industry, they use this reaction, and I'd probably recommend you learn about this one. So you've got to buy this expensive chemical, then it's in a solution of ether. I don't know what ether is, don't ask me, but in an ether solution, then once you've done all that, you need to treat the product with an acid. Yeah, so a bit involved, not very specific, expensive. I wouldn't bet on having to know that one, but I've just written it there for completeness, you know? Seeing as we're going to be here all day. Did I put that one on the... Let's put that first one on the big picture. So that's reacting with hydrogen, not lithium aluminium hydride. Let's ignore that one. But the reaction of a nitrile with hydrogen, reduction reaction, and remember our conditions are metal, catalyst, heat, pressure. I'll do TP like I have, temperature, pressure, yeah? TP. Okay, we're getting there. That's it for nitriles, just reduction reactions, yeah? These are exciting. Alcohols. And we're going to touch on aldehydes too, so just do a little, and aldehydes. So, the key type of reaction we're going to talk about, we're just talking about reduction, but we're going to be talking about oxidation, so just the reverse, loss of electrons, yeah? And you can show all this using your oxidation states and everything. But basically, alcohols, primary or secondary alcohols, not tertiary alcohols. The idea is primary or secondary alcohols are chemically reactive and they have, you know, certain physical properties because the hydroxyl group is not too shielded, you know. It's kind of open to interact with other things. It's out there, but the minute I chuck in a methyl group there, this is now a tertiary alcohol, there's a lot of crowding happening around this and it doesn't readily react. So that's something to keep in mind. Primary or secondary will be oxidized, tertiary won't be oxidized. And because there is still some degree of shielding, you know, and they're different molecules, a primary and secondary alcohol will be oxidized in different ways, so keep that in mind. But we're actually going to treat them as different compounds, I guess. If we oxidize a primary alcohol, yeah, oxidize that, we're going to end up with an aldehyde. If we oxidize the aldehyde, we're going to end up with a carboxylic acid. Now you can sort of see this reaction happening. Say we draw an alcohol, CCCOH, primary alcohol. We're going to oxidize this. Oxidation is loss of electrons. Now this is going to involve that hydrogen atom disappearing, loss of electrons. It doesn't just disappear into the void. Remember, these are only half reactions. There's going to be a reduction half reaction, which I'll talk about in a second. But this is kind of what's happening. This hydrogen is getting lost. We're losing an electron. Primary alcohol, the hydroxyl group is on the end. Aldehyde, the carbonyl group, is on the end. The carbonyl group is on the end. On the end, on the end. Aldehyde. Now, if I oxidize a secondary alcohol, I get a ketone. And you might see what I mean. Let's draw a secondary alcohol. I'm removing this hydrogen and forming a double bond. Carbonyl group in the middle of the chain, it's a ketone. To be an aldehyde, the carbonyl group needs to be at the end of the chain. So a secondary alcohol gives me a ketone. Primary alcohol gives me an aldehyde. Now the important thing about that is aldehyde can be oxidized into a carboxylic acid. Ketone cannot be oxidized further. Yeah? Now, the key condition for both of these reactions is we need a reducing agent. These are only half reactions. And the reducing agents that we use, and for this reaction, are what we call acidified dichromate and acidified permanganate. So, what do I mean by acidified? These are oxidizing agents. They are the other half of each of these reactions. In order to be an oxidizing agent, they have to themselves be reduced. So these give us the reduction half reactions. And if you look in your data book, you can find the reduction reaction for acidified dichromate. You can find the reduction reaction for acidified permanganate. And why acidified? Well, this is dichromate, Cr2O7 minus, and the reduction half reaction has hydrogen ions as a reactant. So you're going to need to be operating in acidic, in fact, 14 hydrogen ions. That's your reduction half reaction. Cr2O7 plus 14 hydrogen ions. Very acidic. You need acidified potassium dichromate. Same thing for potassium permanganate or permanganate ions. So MnO4, that's permanganate minus, and you need 8H plus. Oh, and I forgot the electrons. So remember, reduction is gain. Yeah, and then, you know, you can find the rest of the equation in your data book. And if you're familiar with balancing redox equations, so say you're given a primary alcohol and you're given, you're forming some product, you know, you've got your oxidation half reaction, or you can find that, yeah? And you've also got your reduction half reaction from your data book. So hypothetically, a very hard question could be, you know your oxidation half reaction now, take your reduction half reaction from the data book, and you could write a full, you know, chemical equation by balancing the redox reaction. that's not really what we're concerned with here. The significance of this, right? These reactions are very important laboratory tests to tell apart primary alcohols from secondary alcohols, from tertiary alcohols, and to tell aldehydes apart from ketones. So, let's just think about, okay, this is we've got a beaker, and we've filled it with acidified potassium dichromate, for example. Now, I don't have enough colours for this, but acidified potassium dichromate has a yellow colour. Yellow colour. Now, if we have a solution, and we're not sure whether it's a primary alcohol, a secondary alcohol, or a tertiary alcohol, if we drop in a tertiary alcohol, no reaction is going to happen and the solution is going to stay yellow. So tertiary alcohol is not oxidized. So if it stays yellow, we know we've got a tertiary alcohol. Whereas if it turns green, which is the color of chromium ions that are formed when the reducing agent, the oxidizing agent, dichromate, is reduced. So we're using a dichromate oxidizing agent. If we add in our, unknown solution and it turns green, then the dichromate has been reduced and the primary or secondary alcohol has been oxidized. Therefore, we have a primary or secondary alcohol, so we can tell them apart. Same thing for aldehydes and ketones. So if I had my yellow dichromate solution, acidified dichromate, and I poured in some ketone doesn't get oxidized. So it would just stay yellow. Whereas if I poured in some aldehyde, a reaction is going to happen. So I'm going to get a color change to green because the oxidizing agent, dichromate, will be reduced and change color. There is a similar thing for potassium permanganate. So permanganate starts off purple, and no one can really agree on what color it turns to. It might turn to a pale pink. It might turn brown. That's alcohol. So let's write these down. And the important condition here, really the only condition, they are readily oxidized, but you need an oxidizing agent. So the condition for both is that, for all of these, is that the oxidizing agent is acidified dichromate or permanganate, acidified permanganate. That's your condition. So, let's put all these in. Alcohol to aldehyde, alcohol to ketone. So that's got to be that's oxidation, both of them. And you need acidified dichromate / permanganate. But this one occurs for primary alcohols at the end of the chain, aldehyde. This one occurs for secondary alcohols in the middle of the chain, ketone. And aldehydes can be oxidized into carboxylic acids. And that's the same idea. So oxidation, and you need acidified dichromate again, to be asked to write the whole equation, unlikely. You'd be balancing redox, but you need to know that this is a reaction that will readily happen. The condition is you need an acidified dichromate or acidified permanganate oxidizing agent. That's your condition. Okay. That's it for alcohols and aldehydes. Let's get on to condensation and hydrolysis reactions. So this doesn't really fall under, you know how I talked about, I don't want to go by type of reaction, I want to go by class of compound. Unfortunately, this doesn't really fall under one class of compound because, new page in your notes please, condensation. Because where there's more than one reactant. It's not like, oh, alkane turning into alkene. No, it's, well, one instance is carboxylic acid and alcohol combining to produce ester and water. Yeah. And key thing is, both of these reactions are reversible, and we call the reverse process hydrolysis. And you'll see why in a second. Hell, you'll see why we call it condensation. So, very important reactions. Let's start off with that first one, carboxylic acid, okay? So let's get propanoic acid. Yep. And, ethanol. What is a condensation reaction? Condensation reaction in general is the removal of a small molecule to form a bond between two larger molecules. So the small molecule, and the reason we call it condensation, the small molecule we form is normally water. So we're removing a water molecule, and what happens is the hydroxyl group in the alcohol gets removed, and the hydrogen in the hydroxyl group on the acid gets removed. We now form a bond between this carbon chain and this oxygen atom, and we've just removed H2O. We've formed water, condensation. So what have we formed? We've formed an ester. CCC, double bonded to O, OCC. This functional group here, that's an ester bond, ester functional group. And what would we call this? So, we've got propanoic acid plus ethanol gives us, main carbon chain here, well hang on, main carbon chain here, so it's propanoate. Remember the suffix for ester is propanoate, but we've got a methyl group. Methyl propanoate, we call it. So let's write a word equation for that and get some conditions. Oh, importantly, water. We formed water as a byproduct. I should have written plus H2O at the end there, but we'll write this in the word equation. So, carboxylic acid plus alcohol, reversible reaction, ester plus water, yeah? Because we've removed the small molecule, water. The conditions for this one, in both directions, remember, catalyst increases the rate of the forward and reverse reaction. Heat, acid, catalyst. Yeah? That's synthesis and hydrolysis of esters. We also call the synthesis of esters, the forwards reaction, call it esterification. Formation of an ester, esterification. Okay. How are we going to write this one? Okay, we'll draw an arrow from alcohol to ester. Let's draw a little arrow coming in there as well. And our other reactant, carboxylic acid, also coming in. And I'll just write condensation, heat, acid, catalyst, and I'll put reversible and hydrolysis is the reverse. Yeah, reversible reaction. Our other well, it's still condensation slash hydrolysis. But this time, carboxylic acid. Well, let's draw it. We're forming an amide, so let's draw propanoic acid again. And let's do a secondary amine. So it's NH. Yeah. So propanoic acid plus propanamine, N-ethyl propanamine. Propanoic acid plus N-ethyl propanamine. This is also reversible. Well, what happens here? We're losing the OH, yeah, on the carboxylic acid. We're losing the H here, forming a bond, and we've just removed H2O, haven't we? So we're going to form CCCO. N. So we've just formed a bond between the C and the N, and we're going to have these sticking out. So C, 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 C. Yeah, we've just stuck this guy onto there. And what do we call that? Well, propanamide now, N ethyl, N propyl. N-ethyl, N-propyl, propanamide. So, in other words, carboxylic acid plus amine gives you amide plus water. Remember, very important, we've removed water. Let's write the word equation then. Carboxylic acid plus amine, amide plus water. Now, the condition for this one, it's a kicker. The only condition is a DCC catalyst. What is DCC? Well, it is N-dash dicyclohexyl carbo diimide. You don't need to know that. I really hope you don't need to know that, but you do need to know DCC catalyst. That's your condition. So let's pop that on the diagram. So amine plus carboxylic acid, they're both pointing in, gives us an amide plus water, yeah? And that is condensation. You need a DCC catalyst. Behold, we haven't talked about combustion. If you want to talk about combustion, tell me in the comments. No one's going to watch this far anyway. Combustion's easy. I don't think we need to talk about combustion. But if you have any questions, please leave a comment. Please ask me your questions. yeah, I'm more than happy to answer. I love a question. Even if it's not completely related, if there's something you'd like me to cover, more than happy to cover it. Yeah. I'm gonna upload a photocopy of my, I'll scan a PDF of my A3 sheet. It's a bit neater and it's got more detail. It's got the word equations that we wrote in our separate notes on the diagram. But yeah, that's it.